There are n different types of coupons. One cereal box contains one coupon, and every coupon is equally likely to be present in a box. How many boxes do you need to open before you have at least one coupon of each type? We need to find the number of boxes on average that we need to open before we collect one coupon of each type. This seems similar to the number of trials required before we get a success. So which distribution are we talking about here? Recall that the distribution of number of independent trials prior to a first success is given by geometric distribution. To refresh your memory on geometric distributions, consider a series of trials where the probability of success is p for each trial. What is the probability that the first success occurs at the kth trial? So we have k minus 1 failures first with probability 1 minus p, and then the kth trial is a success with probability p. So this gives us the PMF of a geometric distribution. The expected value of the geometric distribution is given by 1 over p, where p is the probability of success, and the variance is given by 1 minus p over p square. So how does this relate to our problem? We have the opening of boxes, which are the trials, and we have the success criteria, which is finding all the n unique coupons, but we don't know what the probability of success is. So let's go step by step and try to estimate this probability. When the first box is opened, we are sure to get a new coupon because we don't have any coupons yet. So the number of favorable outcomes for us is n, since all of these result in a success, and the total possible outcomes for coupon is also n. So the probability is 100%. When the second box is opened, the probability of finding a new coupon is now reduced because of all the coupon types available. We already have one, so that would not count as a success. So the number of favorable coupon outcomes for us is n minus 1, since all except one result in success, and the total possible outcomes for coupon is n. So the probability becomes n minus 1 over n. We can now generalize this for the ith trial. The probability of finding a unique coupon in the ith trial is given by n minus I plus 1 over n. So we notice that the probability is changing in each trial, and we know that in geometric distribution the probability of success in each trial is the same, so we cannot directly use the expectation for our problem. In such problems where the probability keeps changing in each trial, we need to break it down into smaller sub-problems in such a way that we can use some standard distribution like geometric in this one. So the question becomes, how do we break this down? Let's recall our initial problem. We need to find the number of trials, which is the opening of boxes, needed to collect all the n unique coupons. But for a moment, instead of thinking of collecting all the n coupons, let us think of collecting only the first coupon. And let's denote this by random variable x1, which is the number of trials needed to collect the first coupon. As seen previously, for a geometric distribution, the expected value of number of trials for first success is given by 1 over p, where p is the probability of success. So when we are focused on collecting just the first coupon, what's the probability of success p? Since all n coupons are favorable to us because we haven't yet collected any coupon, the probability of success p is given by n over n, which is equal to 1. So the expected value of number of trials is given by 1 over p, which is also equal to 1. Similarly, let x2 be the number of trials needed to collect the second unique coupon. What's p in this case? Well, since we already have one coupon, the favorable outcome for us is reduced by 1, so we have n minus 1 over n. So now we can generalize this for the ith coupon. Let xi be equal to the number of trials needed to collect the ith coupon. So the probability in this case is equal to n minus I minus 1 over n, since we would have already collected I minus 1 coupons. So now our original problem is broken down into subproblems. The number of trials needed to collect n unique coupons is equal to the number of trials to collect the first unique coupon plus the number of trials to collect the second coupon, and so on till we collect the nth coupon. Note that first, second, third here refers to the unique coupon types. We can write this in terms of our random variables. The number of trials to collect n unique coupons was x. The number of trials to collect the first unique coupon, x1. Trials to collect the second coupon, x2. Similarly, trials to collect the nth coupon is xn. So now we can take the expectation on both sides of this expression. Taking expected value on both sides of this equation, we have expected value of x equal to expected value of x1 plus expected value of x2 up till expected value of xn. And we know that expected value of xi is equal to 1 over pi, as seen previously, where pi is the probability of success. And we have seen that the probability of success pi was n minus I minus 1 over n. So we put the value of pi for all the expected values in this equation to get the final answer, which is the expected value of x is equal to n times 1 plus 1 over 2 plus 1 over 3 up till 1 over n.